This lecture is going to look at the characteristic equation. So first off, just a recap of some of the stuff that we've seen. So if we have a couple of matrices, we've seen that a matrix is invertible if and only if its determinant is non-zero. We've seen that if you want to take the determinant of the product of matrices, it's the same as taking the determinant of the two matrices separately and multiplying them together. We've seen that the determinant of the transpose doesn't change the determinant. If you have a triangular matrix, the determinant is the product of all the entries on the main diagonal. And we've also seen how the determinant is impacted by row operations. So the elementary row operations, if you do a row replacement, it doesn't change the determinant. So in other words, this is where you take row 3 plus row 2 is the new row 3. That doesn't change the determinant. If you change two rows, so exchange row 1 and 3, the determinant becomes the negative. And if you scale, so if you take row 2 times 5, the determinant changes by a factor of 5. So this is just summarizing a few things we've seen about the determinants that are going to come into play when you start looking at characteristic equations and determinants for determining eigenvalues. So we've already talked about eigenvalues. What is the characteristic equation? The characteristic equation is the thing that lets us find eigenvalues. So we've seen that an eigenvalues of a matrix satisfy the determinant of A minus T in equals 0. In the last lecture we saw it written as minus lambda I, but we're just using a different variable name here. Often when you see the characteristic, you will use a slightly different variable name. You'll use the T instead of the lambda. Just a bit of a convention. Not all books use it, but you'll often see it written that way. So this equation, when you take a matrix, subtract T times the identity, and then calculate the determinant. Now remember the T in there is a variable, so we don't have a specific number for it. It's just a variable. When you take the determinant of that, that is called the characteristic equation. And we often talk about the characteristic polynomial being just that without the equal to 0 part. So for example, what do I mean by the characteristic equation? Well, here's a simple matrix. When we want to find the characteristic equation of A, we're looking for the determinant of A minus T times the identity, the 2 by 2 identity. So in this case, it's 4 minus T, and you leave the variable in there, 2 minus 3 minus 1 minus T. So what's the determinant of this? Oh, sorry, it's the determinant of that. So the determinant of that is 4 minus T times negative 1 minus T minus negative 3 times 2. Now let's multiply it all out and simplify. So this is negative 4 plus 3t, that's 4t, it's minus 3t, sorry. Plus t squared plus 6. So it's equal to negative 3t plus, oops, let's rewrite that a little bit just to put it in a more conventional form. It's equal to t squared minus 3t plus 2. And this, if you're used to polynomials, you can take this and you can factor it. That's equal to t plus t minus 2 times t minus 1. So what does this mean? This means that the eigenvalues of A are the solutions to t minus 2 times t minus 1 equals 0, or t equals 2 and t equals 1. That's the two eigenvalues of that matrix. So the characteristic equation is this. T minus 2 times t minus 1 equals 0. So what about the characteristic polynomial of this one? Well, if we do this one, we're looking for the determinant of 4 minus t, 0, 8, 2 times 7 minus t, 8, 0, minus 2, and minus 3 minus t. Now, when we're looking for the determinant of this, we can use the expansion of it. So that's equal to, go across the first row, 4 minus t times negative 1 to the 1 plus 1 times the determinant of that plus 2 times negative 1 to the 1 plus 2 times the determinant of 0, 8 minus 2 minus 3 minus t. So that's the determinant. And then the third term is 0, so we don't need that. So now we take this and we simplify it. So this is 4 minus t times negative 1 to the 2 is just 1 times the determinant of that. 7 minus t, which is 7 minus t minus 3 minus t plus 16. And then this becomes minus 2 because it's 2 times negative 1 raised to the 3 times the determinant of what we have there. And you see that is 0 plus 16. So it's that. So let's simplify. 4 minus t times, combine everything in here. We have negative 21. Let's see, that'll be plus 3 minus 7, so minus 4t plus t squared plus 16 minus 32. And now we just keep doing some simplifications and see what we get. So I'll just combine the terms here. Minus 5 minus 32. And now let's multiply this out. We get 4t squared minus 16t minus 20 minus t cubed plus 4t squared. Oops. 4t squared plus 5t minus 32. Let's combine some terms here. We get minus t cubed. We have 4t squared plus 4t squared plus 8t squared. For the t's, we have minus 16 and 5t, so that becomes minus 11t. And then minus 20 minus 32 is minus 52. So unless I did some of the algebra wrong here, that is our characteristic polynomial. Okay, so if you have that characteristic polynomial and you can figure out from that what the eigenvalues are. So if you have a characteristic polynomial to the power of 2, you can use the quadratic formula to figure it out, or sometimes you can see if you can factor it. But in any case, you can figure out what the eigenvalues are. If an eigenvalue is repeated, then we say that it has a multiplicity. So the multiplicity of an eigenvalue is the number of times the term appears as a factor in the characteristic polynomial. So what does this mean? So for instance, here's your matrix A. You figure out the characteristic polynomial of this, you're going to boil it down to that. That means it has two eigenvalues, eigenvalue of 2, eigenvalue of 1. Each of those terms only appear once in that quadratic, in that polynomial. That means they each have multiplicity 1. However, if you take a look at this second matrix and work out its characteristic polynomial, you get t plus 1 squared and t minus 3. What does that mean? That means that you have two eigenvalues. The first eigenvalue has multiplicity 2. The second eigenvalue has multiplicity 1. So it's the number of times a term appears in the characteristic polynomial when you can factor it right down. Another example, if you have a characteristic polynomial that's this, much larger, more complex, eigenvalue 4 has multiplicity 3 because it's raised to the third. Eigenvalue negative 2 has multiplicity 2. And eigenvalue of the eigenvalue 3 has multiplicity 1. So that's what multiplicity is. It's the number of times that a term appears in the characteristic polynomial. And we're going to see later that this actually has more meaning beyond just being the number of times it appears. It actually impacts on the eigenspace. That's for a later lecture. So for instance, we have this. Here is a matrix. We're going to find the eigenvalues of this, their multiplicities, and a basis for each eigenspace. So first off, we have to find the determinant of 2 minus t, 0, 0, 1, 1 minus t, 0, and 0, 2, 1 minus t. That's finding the characteristic polynomial. But now remember that when you have a diagonal matrix, the determinant is just the product of everything along the columns, or along the diagonal, the main diagonal. So this one is easy. 2 minus t times 1 minus t times 1 minus t, or 2 minus t times 1 minus t squared. So we have two eigenvalues. Eigenvalue 1 is 2 minus is 2, and it has multiplicity of 1. Our second eigenvalue is 1, and it has a multiplicity of 2 because it appears twice in that equation. So now the next step is to take these eigenvalues and figure out a basis for the eigenspace. So that was our matrix. And first off, we're going to look at the first eigenvalue, which was 1. And remember, this had a multiplicity of 1. So what do we have to do? To find this out, we have to find the null space of our matrix minus 1 times the identity. So it is going to be 1, 0, 0, 0, 0, and 0, 2, 0. So we have to find the null space of this. Now notice that this is going to be pretty easy here. If we look at this, we do our row reductions. We're almost there anyways. We are going to get very easily with 1/2 row 2 is the new row 2. We are down to a row reduced echelon matrix. So now from here, we assign an x1, x2, and x3 to each column. We have the equations that x1 plus x2 equals 0, x3 equals 0. We have x2 being a free variable. So this gives us x1 is equal to negative x2. x2 is free, and x3 equals 0. So our vector form for the equation is x1, x2, and x3 equals. x2 is our only free variable, So it's x2 times something. It's -1, 1, 0. That's our vector form. So our basis is -1, 1, 0. There's the basis for our first eigenspace. That is the basis for the eigenspace associated with the eigenvalue of 1. So now we're going to look at the second eigenvalue, which is the eigenvalue of 2. So we look at our matrix minus 2 times the identity. So we are going to need to find the determinant, or sorry, we are going to have to find the null space of 0, 1, minus 1, 0, 2, minus 1 of that matrix, which our original matrix minus 2 times the identity. So let's take our matrix and we're going to row reduce. So row 1 plus row 2 is the new row 2. And then we're going to do row 2 plus 2, row 3 is the new row 3. And then we can just take 1/2 of row 2. Oops, that's a 0 in there. There. So that's the row reduced echelon form. Now we have our 3 variables again, x1, x2, and x3. We can see that x1 is a free variable this time. So our equations associated with this matrix are that x2 equals 0 and x3 equals 0, which if we put into our normal form, we have x1 equals x1, x2 equals 0, and x3 equals 0. In vector form, we now have x1, x2, and x3 is equal to x1 is our free variable times 1, 0, 0. So our basis for this eigenspace is equal to 1, 0, 0. There is our basis for the eigenspace. Okay, so that's the idea of using characteristic polynomials to find your eigenspace, your eigenvalues, or first your eigenvalues, then your eigenspace, and the idea of multiplicity, how many times it appears, how many times each term appears in your characteristic polynomial. And as I said, multiplicity, we're going to use it again at a later point. Here's another definition, the idea of similar matrices. Okay, so a similar matrix means that a matrix A is similar to a matrix B if A is equal to some matrix times B times the inverse of that matrix. We call those similar matrices. And we're going to see that similar matrices share a lot of properties. So they don't look the same. By glancing at the matrices, you probably wouldn't be able to tell that they are similar, but they do share a lot of characteristics in common. So we're usually interested in similar matrices. One thing to note is that if A is similar to B, we also think that B is similar to A. Why is that? If we have A equals P times B times P inverse, multiply both sides by P. We have A times P is equal to P times B times P inverse times P. So we just multiplied the right-hand side by both. Well, that's just the identity. So that means that A times P is equal to P times B. Note that this is another concept of similarity. And remember how we talked about how matrices, it matters what order you put them in? A times P equals P times B. That is another definition of matrices being similar. You see that they are equivalent. It's just a different way of writing the same equation. But now let's take this one step further. Let's multiply both of these things by P inverse on the left side. We have that P inverse times A times P is equal to P inverse times P times B. But look here, we have the identity matrix. So we have that B is equal to a matrix times A times the inverse of that matrix. It just so happens that it is the same matrix we used earlier, just kind of in a different order. So if we say let Q equal P inverse, then we get that B is equal to Q times A times Q inverse, because the inverse of an inverse is the original matrix. Okay. Another note for something we're going to use later is that there's this idea of powers with a matrix. If A is similar to B, then A raised to the n, which is A times A times A times A, n times, is similar to B raised to the n. And why is that? We can see why. If we have that A is equal to A is similar to B, then what happens with A squared? So what's A squared? That's just A times A. So that's equal to P, B, P inverse times P, B, P inverse. That's just replacement. But now gather up the terms a little differently here. We have PB times P inverse P times B, P inverse. But notice what we have in the middle is the identity. So that's just equal to P times B times B times P inverse, which is P times B squared, P inverse. And you can continue that for any number of exponents. So theorem 4, here's the first thing that we see about similar matrices. They actually have the same eigenvalues. Similar matrices have the same characteristic polynomial, but remember we saw how if you get the characteristic polynomial, you can get the eigenvalues. So if they have the same characteristic polynomial, it means they have the same eigenvalues. Now, just a note here not to get this mixed up. If two things have the same eigenvalues, it doesn't mean they're similar. They might be, but they don't have to be. Okay? Similar means they have the same eigenvalues. It doesn't work the other way. So why is that? Well, here's the proof of why, if you start out with two matrices that are similar, they have the same eigenvalues. So if they're similar, that means you can write them this way, that B equals P inverse times A times P. How do you get the characteristic equation, the characteristic polynomial for B? You take the determinant of B minus lambda times I. But what's B minus lambda I equal to? Well, B is equal to P inverse AP, so just replace that. The identity, we can rewrite that as P inverse times P, because we know P is an invertible matrix. Any matrix times its inverse is the identity. So we've just rewritten and did a couple of substitutions here at first. Now let's gather up the terms. First off, notice that lambda is just a number, so you couldn't actually take that inside there. So I'm just rewriting this. I'm taking the P inverse out because the P inverse is on the left of all of these. It gives AP minus lambda times P. Again, this works because lambda is just a number. But now note you have a P on the right-hand side, so I can rewrite it that way with the P on the right side. And notice what I have now. I started with B minus lambda I. I've ended up with an A minus lambda I right in the middle. So that means that B minus lambda I, remember that's just a matrix, is similar to A minus lambda I. But now take this thing on the right-hand side and use the properties of determinants. So the determinant of b minus lambda I, that thing on the left side, is equal to the determinant of p inverse times a minus lambda I times p, this thing on the right-hand side. But what's the determinant of that? Remember, we said that if you have matrices that are multiplied together, you can take them apart and do the determinants of each individually. So what's the determinant of p inverse times the determinant of a minus lambda I times the determinant of p? But now, remember another property of determinants, that the determinant of an inverse is equal to the inverse of the determinant. So the determinant of p inverse is equal to 1 over determinant of p. So that means this term and this term cancel out, and you're left with the determinant of b minus lambda I is exactly equal to the determinant of a minus lambda I. And that's your characteristic polynomial. So the characteristic polynomial of b is the exact same as the characteristic polynomial of a. So when you have similar matrices, remember I said that similar matrices means that they have a lot of properties in common. One of the more important properties they have in common is the characteristic equation, which means their eigenvalues are the same. So let's look at the characteristic equation. We are going to look more closely at determinants and some other properties of eigenvalues and some other properties of eigenvalues and eigenvectors.